year 3, or really year 3.5 of our 5 years, we intend to collect data, at least in the ocean, through 2020. And there's several different pieces, but the basic idea is that we know, as I said before, we know Greenland's melting. If you look at the patterns of ice loss that come from the GRACE satellites, which measure mass change and mass redistribution across the Earth, we can see that the places where Greenland is kind of melting the most quickly are the northwest, which is an area where lots of the glaciers reach the ocean, and also the southeast, which is another area where you have a whole lot of glaciers that are grounded below sea level and actually touch the water in both of these places. So with OMG, what we're really trying to do is measure both the oceans and the ice together over a period of 5 years, and try and ask the question or answer the question: how can we relate these ocean changes that we see to ice changes around the margins of Greenland? One of the primary things you have to figure out if you're going to understand how oceans and ice interact is the geometry of how these things are situated. As you'll see in some later images, the continental shelf surrounding Greenland is incredibly complicated, and there's all these troughs that were cut by ancient glaciers. And these allow pathways for the water to reach in and interact with the ice. But if we don't know the shape and depth of the sea floor, we're really at a huge disadvantage. So a lot of our early work in OMG was really to just try and measure the shape and depth of the sea floor. So we had 2 different bathymetry campaigns. I'll describe them in a second, but they're both finished, and all the data is available, and we're still processing some of it. If anyone is interested, probably the most important thing that I'll say in this entire thing is that all of our data is online pretty much as soon as we can quality control it and make it scientifically usable. There's no waiting period, so everything that we have, you can go to the website omg.jpl.nasa.gov and download by clicking on the Data tab. So please go check out the data. There's a whole lot of it now, and we're really just beginning to scratch the surface of it. So why do we care about Greenland? Of course, sea level rise is one of the major impacts of human-caused climate change, and this is actually one of my favorite time series in climate science because it shows essentially the hockey stick of sea level rise. This is actually from data collected off the coast of North Carolina. These are salt marshes where they drill down and reconstruct sea level rise. And essentially for 2,000 years, you have almost nothing going on, and then you have this really rapid rise right at the end, which coincides with which agrees with local tide gauges through this period. And the rate of rise is faster than anything now, is faster than anything in the last 2,000 years. And this is relevant because, of course, Greenland is capable of discharging a huge amount of ice and raising sea levels by a really substantial amount. I mentioned GRACE earlier. This is a pair of satellites that measure the mass change. The original GRACE satellite died 1.5 or 2 years ago, and the follow-on just launched earlier this year and is.
Please stand by while your recording connection is established.
But if you look at the patterns again, most of the ice loss is around the margins, and a lot of it is actually concentrated in
this conference is being recorded.
Ah, good. Our recording's up. Great. This region right here is actually centered on Jakobshavn, which is one of the biggest glaciers, the biggest glacier in Greenland, and we have some interesting results centering around there, which I'll talk about in a second. But essentially, we can use GRACE to quantify the mass loss, and it's almost 4 trillion tons since the beginning of the record in the early 2000s that Greenland has lost. And if Greenland was to lose all of its ice and instantaneously, of course, it would raise sea levels by 24 feet. We don't think that's going to happen, but how fast this ice is lost is really a central science question for climate science today. So how are we addressing it? Well, I mentioned that we needed to measure the seafloor shape and depth, and we had two observational campaigns to do this. One was a ship-based multi-beam sonar survey. This was a survey of the seafloor depth directly, very high resolution. I think it's 5 or 10. I think we have 10-meter postings available on the website. Very high resolution. Of course, the ship can't cover the entire continental shelf, and so we had to supplement in certain places with airborne gravity measurements. These gravity measurements, as the plane flies over, if there's a trough or some deeper area, then the pull of gravity is actually slightly smaller. The gravimeters aboard, the accelerometers aboard the aircraft measure this, and you can invert that and reconstruct the shape and depth of the seafloor. So we have these two campaigns. Both of them are completed a couple years ago now, and the data is all available on the website. We're still working to do the inversions of the gravity to make improved maps of the seafloor, but we hope to have, by the end of the calendar year, seafloor maps that include both the gravity and the sonar. The other half of the OMG mission, which is really the central part, is two campaigns to measure the ice height changes and the ocean temperature changes offshore. These are both conducted by aircraft. The ice survey is an airborne radar. It's a swath altimeter, an interferometer, so it measures essentially sweeps out a swath, creating a digital elevation map. The spatial resolution that we get is on the order of 3 meters. A bit of averaging is necessary, so we tend to look at 15 or 20 meter postings in order to get a little smoother signal. But you can see fantastic detail in these of the glaciers. The swath is about 10 kilometers wide, and we try to cover the last 10 kilometers, 5 to 10 kilometers at least, of all of the marine terminating glaciers in Greenland at least once per year. We began in 2016, 2017 was completed, and 2018 was completed this year. So we have 3 years of data for most of the glaciers. 2016, we missed some of the Northwest because of an instrument issue, but we have 3 years of data for a large number, for almost all the glaciers around Greenland. The other half of the survey is an ocean-borne survey. So essentially, we drop expendable CTDs from the aircraft. There's about 250 of these that we drop each year. The probes fall from the plane. There's a small parachute. They land in the water, and then they sort of split into two pieces. One part is a float that stays near the surface, and the other part is a small probe shaped a little like a torpedo that falls on a wire and measures temperature and conductivity as it goes as a function of time. They fall at a fairly carefully calibrated depth, and all of this information is radioed back to the airplane in real time. So we actually watch the probes trace out the temperature and conductivity as they go. The other thing that's important about the glaciers in Greenland is that most of them are what are called tidewater glaciers. These are glaciers that sit in narrow channels for the most part, and they typically meet water on the continental shelf that is what I like to call upside down. So in oceanography, in most places in the world, the warm water is on top and the cold water is on bottom. But on the shelf, it's the other way around. The cold water is mostly from polar origins, from the north, which are very fresh. The warm water is from the south, which is very salty. And so you have this inverted temperature structure in contact with the glaciers. And the interface tends to be around 150 or 200 meters. It varies a little bit over time and space, but by and large, we're trying to look for this warm water, which is down 150 or 200 meters below the surface. And that's the reason we really have to use some kind of in situ observations as opposed to a remote sensing solution, because we really have to measure these deeper waters, in order to really understand how the oceans are affecting the ice. Just to give you an idea of what this looks like, I'll play this movie really quickly. This was the very first test that we did, dropping the probes out of the Gulf Stream 3, which we used in the first year of the survey. These are NASA aircraft, and this is a small chase plane that's following us around with a photographer. The photographer filmed the probe leaving, which is what this looks like, and essentially trying to make sure that the probe didn't hit the bottom of the plane. And if you look really carefully, right at the end, I'll just play this part again. If you look really carefully right at the end, you can actually see the parachute open in one frame right there. So this parachute opens and allows the probe to hit the water at a relatively mild 60 miles per hour. They still hit pretty fast. Anyway, yeah, if you want to see more videos and stuff of the mission and what it looks like when we're in the field, I maintain a Facebook page. It's facebook.com/climateelvis. If you get a look at my sideburns, you'll understand the moniker. But if you're interested in kind of what the campaign looks like visually, I try to post a lot of videos and movies from our field time there. So these are what the ocean and ice campaigns look like practically. The yellow dots here are AXCTD drops. We've hit most of these in 2016 and 2017. We also had a ship survey in the Northwest in 2015. And the red lines are where we measure the ice heights. Some of these are a little. This is a little bit of an old plan. And if you go look at the data on the website, you'll see that instead of these short little lines, a lot of them have been replaced by 2 or 3 long straight lines. But nevertheless, we have a lot of data covering the margins of the ice, which I'll talk more about in a second, and 2016 and 2017 ocean observations in patterns similar to this. The right-hand side shows our bathymetry campaign. The yellow is a ship track, and the green is where we have airborne gravity observations. And these have really provided fantastic detail in a lot of regions, and also some of our early really important results, which have been published by Matthew Morligam at UC Irvine. He took our bathymetry that we measured from the ship and combined it with bed topography under the glaciers and made a product called Bed Machine, which is a continuous product across the ocean ice boundary. So we know the shape of the bathymetry continuously from under the ice to where we've observed it in the seafloor. It's a sort of interpolation across the ocean ice boundary, and it's shown some interesting results too, in that there are a whole lot more glaciers than we previously knew that are connected to the ocean by deep pathways. So that means there's a lot more glaciers that are really threatened by ocean warming than we previously knew. This is one of the early important results from OMG. Yeah, this is a little more detail on what I just described. This is Bed Machine, which you can download this data from the UC Irvine website. And essentially, it's what I just explained. It's a connection between the ocean observations, which are shown here on the left or sort of center panel, and estimates of the bed topography underneath the ice, which is on the right panel. And then the lower left is is the interpolated product, which is continuous over the whole region. This is what the GLISTEN survey, the ice survey, really looks like. The red lines here are all the 2017 lines. We also have 2018 lines over these now. And the data looks something like the panel on the left. This is a wrapped color scale, so every 50 meters it repeats. So when you see the sort of lines going perpendicular across the swath, that's an indication that the elevation is changing really quickly. Further out on the swath, this is actually Petermann Glacier, which has a large ice tongue. This is a large flat ice tongue, which is floating, and there's some really fantastic detail in this data as well. The OMG website links to another website where you can download and actually view all the data. It's pretty impressive just to go kind of click around and have a look at this some of this data visually. But of course, we hope lots of folks are downloading it and playing with it too. These are our ocean campaigns between 2015, 16, and 17. You can see the ship observations in 2015, and then 2016, 2017. In the last year, 2017, we got out pretty late into the season, and sea ice was beginning to form in the north and northeast. So we missed some observations in 2017, although we hope in 2018 to go back and fill in all those gaps in a couple of months when we're back out. These are some early results from a paper that was just published in Oceanography. It's actually published now. If you Google search for it, you can find it. Essentially, it was an analysis of two small glaciers in the far northeast corner of Greenland, in this long fjord called Ingelfeld. And at the end of the fjord, there are two glaciers, Tracy and Helprin. Tracy has receded very rapidly. In fact, it's been receding for about 100 years. There are estimates of the front position all the way back in the early 1900s. And Helprin, which sits right next to it and encounters presumably the same atmosphere and more or less the same ocean, is actually not retreating. And so we looked carefully at the data. We had a lot of ocean data in here, mapping out the seafloor depth and also collecting temperature and salinity observations. And we found this sort of interesting story that the two glaciers are behaving very differently. This is a digital elevation map constructed with the GLISTEN data from 2016 in a swath over Tracy and Helprin. You'll kind of see where it is in a second. But if you look carefully at the fronts of Tracy and Helprin, this is 2016, and if I scroll forward to 2017, you can see that the front of Tracy has actually receded a little bit in 2017, and Helprin has stayed almost exactly the same. So if I just go back and forth a couple times, you can sort of make out the changes. And what's interesting is if we quantify this by looking at the actual difference between the 2 years, you can see that Tracy is actually thinning very rapidly by about 10 meters, 10 or 12 meters, and has receded. While Helprin is thinning, it's only thinned by a meter or two in the same time period. And so we looked at the oceanographic data. There were a lot of CTDs collected in this fjord, and found that the ocean circulation kind of travels in this counterclockwise pattern, water coming in along the southern edge, circulating past the two glaciers, and then heading back out. And if we look at the temperature and salinity data in these regions, I'm going to skip ahead a little bit, we can see that the sort of upstream waters, upstream of the two glaciers, have a very classic structure. The blue profiles shown on the left-hand panel show the water structure for the upstream profiles, and the red are essentially downstream of the two glaciers. And what we see is that as the water passes by these two glaciers, it's modified very strongly in about the 100-meter depth layer. And what we believe is happening is that the runoff from underneath the glaciers, essentially surface melt is collected across the ice sheet in a network of moulins, and it runs down to the bed and then eventually out back to the ocean. So this fresh, cold meltwater is essentially running off from underneath these glaciers, encountering the ocean water, which is heavier, and rising along the face of the glacier in a plume. And so what we believe is happening here is that the plume is essentially mixing water from the warmer, deeper parts of the water column into this sort of 100-meter layer, and modifying the water pretty dramatically downstream of Helprin. and Tracy. And if we if we do a very simple 1D model of that plume, it suggests that, in fact, almost all of the action is happening in front of Tracy. And the reason for that is that the Tracy Glacier sits in about 600 meters of water, and the Halpern Glacier sits in only about 350 meters of water. So the primary difference between these two is really the amount of water that each one is exposed to. And that seems to be consistent with other findings as well, suggesting that it's really the ocean that's driving Tracy to retreat so quickly, and that because of its much smaller exposure to the ocean, Halpern is really not reacting very quickly. This is the plume model. I think I'll skip over it and talk about Jakobshavn for just a second. This is a new result that we're still revising right now. It's been through one round of review at Nature. I'm not sure if it'll wind up in Nature, but we're pretty optimistic that it will get published soon in some journal. But essentially, what we've seen at Jakobshavn is rather surprising. I mentioned earlier that this is the biggest glacier in Greenland. It's been retreating for about 20 years, pretty steadily for about 20 years. And it was responsible for that giant mass signal in the GRACE data that I showed right at the beginning. So we know it's shrinking, but it turns out in the first 2 years of OMG, this is the digital elevation map of Jakobshavn. You can see it kind of winding its way from the bottom of the screen up towards the sort of middle. And if we look between 2016 and 2017, here's 2017, Jakobshavn actually advanced by about 4 kilometers. And it turns out if we look at the difference between 16 and 17, which is shown in the color map here, green indicates that Jakobshavn actually got thicker. And in fact, Jakobshavn thickened by about 20 meters between 2016 and 2017. And in fact, we've had a look now at the 2018 data, and it's thickened again by about another 20 meters between 2017 and 2018. So suddenly, this glacier, which has been retreating for very steadily for the last 20 years, since the late 90s essentially, has begun to advance and thicken. And the question is why? And so we did a pretty exhaustive analysis. Here's just a profile up and down the glacier showing the change from one year to the next. And between 2016 and 2017, you see this very significant thickening, which didn't happen really any time in the last 20 years. But if we look carefully at the oceanographic data, we begin to get a clue that suggests that, in fact, the water in Disco Bay, which spills over into this fjord and bathes the face of the glacier, has actually cooled between 2015 and 2017 pretty significantly by 1.5 degrees. And we've looked at this signal in Disco Bay, but also sort of upstream in a variety of places and in a variety of different data sets, and it's fairly robust. There was a pretty clear cooling of this deeper subtropical water that flows into Disco Bay and eventually reaches the glacier. And it coincides perfectly with the advance and thickening of the glacier. This is, to make a long story short, we strongly believe that this cooling is essentially what's responsible for the recent advance of the glacier. So this is a surprising result because we expect these glaciers to be retreating. But in fact, as the ocean signals, as the ocean carries time-varying signals of warmer and cooler waters into these regions, we're beginning to see very drastic changes, not just in retreat, but also in advance. So essentially what's most surprising about this work is that it appears that the ocean forcing in this case has been strong enough to overcome this long-term retreat and cause at least a couple years worth of advance of Jakobshavn Glacier. And in fact, some of the preliminary analysis from the 2018 data suggests that it's not just Jakobshavn that's thickening, but other nearby glaciers are either slowing down or thickening as well. Of course, we'll be watching for this ocean signal to see if it spreads northward up the coast as would be expected by the kind of time mean circulation that we know exists there. It's a sort of a pivotal moment for OMG because we're beginning to see the kinds of signals that we really set out to. I think I'll skip over the rest of this and kind of conclude here. This is just a little bit of a preview suggesting that this ocean signal is actually more widespread than just in Disco Bay. If we look at the 2015 ship data and the 2017 airborne cruise in Melville Bay, this sort of corner in northwest Greenland, then we see that cooling signal actually has traveled all the way up the coast. And as I said, we'll be looking for this kind of slowing or in some cases even advance and thickening of glaciers to see whether it spreads up and down this coast. I think I'll stop there. Hopefully you guys can have a copy of this PowerPoint if you're interested. There's all kinds of information on the OMG website. Again, we're about halfway through our 5-year mission, and we're beginning to see some really exciting, interesting results. You know, I said at the beginning of the talk that the main science goal is really to measure the oceans and measure the ice and then ask how the changes are related. And it appears that we're really beginning to be able to see that in our here in our 3rd year. So we're excited about the last couple years of our mission and looking forward to some more exciting results. Just as a little bit of fun before you guys ask me questions, I also will just, for those who are interested and know me, I do a lot of outreach and communication on climate change. And I recently made a video that's kind of fun, and you should check it out. If you Google Climate Elvis, you can see me embarrass myself quite thoroughly with my big sideburns and Elvis costume, singing an Elvis song about the climate and why it changes. And I'll stop there.